Welcome to Pomodoro Joe for Sunday, August 27th, 2023. Today we're looking at LeetCode problem 403, frog jump. This is a hard problem. A frog is crossing a river. The river is divided into some number of units, and at each unit there may or may not exist a stone. The frog can jump on a stone, but it must not jump into the water. Given a list of stones' positions in units, sorted in ascending order, determine if the frog can cross the river by landing on the last stone. Initially, the frog is on the very first stone and assumes the first jump must be 1 unit. If the frog's last jump was k units, its next jump must either be k minus 1, k, or k plus 1 units. The frog can only jump in the forward direction. Okay, so this actually seems pretty straightforward. I wouldn't consider this hard. This looked more like a medium plus problem. Well, we'll see. Maybe it's harder than I think. All right, so here are our stones. We start at the very first stone, and we can jump 1, and then we can jump either 0, 1, or 2 units. Now 0, it looks like we can't actually do because it says it must jump forward. So we have to go forward. So we can go from 0 to 1, and then 1 looks like we can go to 3, so we can jump to 3. And then we can jump 4, 5, so we can jump to 5. We can actually do 4, 5, 6. So either one, we can do 5 or 6. And then from 5, we can jump 3, so we can jump to 8. And then we can jump either 2, 3, or 4, so that gets us to 12. Since we jumped 4, we can do 3, 4, or 5, and 5 will get us to 17. Okay, so yeah, this seems pretty straightforward. All right, we have up to 2,000 stones. But the stones' positions can be very, very large. So one thought would be just to create a mapping of all the stones using an array, but since these stones can map to very large numbers, I think we'll use something else like a dictionary. All right, we'll put 25 minutes on the Pomodoro timer and we will get started. So if you are familiar with a graph traversal, this seems very similar to a graph traversal, but in a very limited scope where you can only move forward and you can only move to higher valued nodes, these stones. All right, so we'll just consider this a standard graph type traversal. Now we could do this recursively, but I think for me, I generally do graph traversals using a queue. So we'll use a queue for this. All right, so what do we need to do? Well, we'll start our frog at some position, so we'll keep track of our position. That's going to be 0. And we have to keep track of our k. How far can the frog jump? Initially, that's 0. All right. Now we'll jump to a stone. So right now we're just given a list of stones. What I'd really like to know is, given a position, is there a stone at that position? So I kind of want to turn this list of stones into something where I can just do a lookup, like a dictionary. So let's start with a dictionary. So I'll have a stone map. And for that, I'll make it a default dictionary. And let's see, I'll probably use Booleans. So there's either a stone or there's not. All right, so for every stone in our stones, we'll set our stone map for this stone equal to true. So this way I can just take a position, look it up in my stone map, and see if there's a stone at that position. Cool. All right. Now if we treat this as a standard sort of graph traversal, I'll need a queue. So let's have a queue here. And what do we keep in our queue? So the queue will store the frog's current position. All right, so let's have some note here. So this will be a tuple with the position, and we need to know the k, so the frog's jump. So every place the frog can go, we'll have to keep track of not just the position, but also the last jump it did, because that determines how far we can go on our next jump. So we'll have our position and our k. So initially, our frog starts at 0 with a 0 jump. All right, so I actually don't need these out here since I'll be storing these in our queue. So we'll pop some value or state out of our queue. We'll check the values for the position and the k. We'll see where the frog can jump next. So we'll calculate our k plus 1, k minus 1, and k jump targets. Once we have each one of those targets, we can check to see if there's a stone at that target. And if there is, we can add it to our queue. or we could just add it to our queue and then later check to see if there's a stone at that target. Either way, we'll be putting this new state, that's the position and the new k, into our queue for processing later. And we'll just keep popping these out of our queue, basically looking at all the possible places the frog can get. If we end up on the last stone, well then we know we've made it to the end and we can return true. Okay, so while we have some queue, so we'll be processing all these states that the frog can be in. So I'll call this a state. So queue dot will pop at index 0. So now I'm going to do this breadth first, so that's pop index 0. If you want to do depth first, you can pop at index -1. Now, I don't think in this case it'll make a difference because we can't go backwards. There shouldn't be any sort of loops or cycles in our graph. So it probably doesn't matter if we pop at 0 or -1. But for me, I'm going to go with the breadth first, so I'll pop at 0. All right. Now, typically, we also look to see if we've been at this state before. So let's have another thing out here, our visited set. That's just going to be a set. So we'll check to see if this state is in the set. If we've already been in this state, let's not process this again. Now, in this particular problem, it probably doesn't matter. Well, I shouldn't say that. In this particular problem, we don't have cycles, so checking our visited won't block us from getting into cycles, so that's not a problem. But what visited can do is prevent us from processing the same state multiple times, so that could save us a ton of processing. So let's see, if our state is in visited, well then we'll just continue. We don't need to process this state again, we've already done that. Otherwise, we'll need to add this state to our visited. Okay, so that takes care of our visited stuff. Next, let's get the position and our k out of the state. Okay, at this point, we have a couple different things we want to check. The first thing I want to check is my end condition. Is this the final position? Is this the last stone? If it is, then we made it and we can return true. So if our position is equal to, let's see, our last stone will be stones at index -1. And if that's the case, then we can return true. Cool. If we're not at the last stone, then we need to do another jump. Now if, let's see, maybe we jumped too far, so let's also check that. If position is greater than stones at -1, now we've jumped too far and we can just continue. We don't jump again from this position. Okay, what other conditions are there? So now we know our position is actually less than our final stone. So we have three options. We can jump to k-1, we can jump to k, or we can jump to k+1. So let's just explore all of these options. So option 1, this is going to be our k-1. All right, so for this, we'll have some new k, and that's going to be k-1. And we'll have some new position, and that's going to be our current position plus our new k. So this is our jump. So we just did a jump, we're at a new position. Now this new position should be greater than our current position. So if k is 1 in this case, then we might end up jumping to the same stone. We don't want to do that. So we better check if we've advanced to some forward position. All right, let's just double check here. If our new position is greater than our current position, and let's check to see if there's a stone here. So, and let's see our stone map for this new position. So if that's true, then there's a stone there. And now we'll use this new position and this new k, and we'll queue that. So queue.append, now we'll wrap that in a tuple. So we'll have a new position and new k. Cool. All right, so that's option 1, k-1. We calculate our new position and the new k. As long as we're jumping forward and there's a stone there, then we'll queue that new position and the new k. And we'll just do the same thing for k and k+1. So that's option 2 and option 3. All right, so let's look at option 2. Option 2 is just k. So the new k is also just k. Position is position plus the new k. As long as we're jumping forward and there's a stone there, then we can queue that up. All right, and finally k+1. So this is option 3. All right, option 1, option 2, option 3. These are our 3 possible jumps. All right, and I think that might actually do it. Okay, now at the very end, if we get through all of this and we didn't actually return true, then we've exhausted all our possible jumps and we have to return false. Okay, I might be missing some edge cases here, but let's just run this and see how we do. And we pass. All right, let's submit this and see if we can pass all the tests. And we pass. Let's see, we don't do great. We only beat 48% for runtime and 62% for memory, so that's not great. But let's jump back and make a couple changes here. So one thing I noticed, this map, I'm using a default dictionary of just Booleans. Now I'm not actually using anything else other than checking to see if a stone is at this location. So instead of using a default dictionary, I can use a set. So let's just do that. Let's just use a set and we'll pass in our stones. All right, so that's going to help us out quite a bit, I think. We'll find out. All right, and then down here, instead of checking this index new position, we have to check if new position is in the stone map. All right, I'll have to do that for all of our options. Okay, so I think that'll save us a little bit in memory, maybe a little bit in runtime as well. Let's try this. Still works. And we do worse. Now we're at 40, no, we do exactly the same. Maybe a little bit better memory. Interesting. All right, let's jump back here. Okay, one other thing. You might notice that these all look exactly the same. So instead of doing it this way, maybe we could use the same code in a loop so we don't have multiple copies of the same code. So let's try this. Let's have, let's see, offsets. And we can either jump to -1, 0, or 1. These are our offsets from our k. And I'll say for offset, in our offsets. All right, so the new k will be k plus our offset. And then all of this does the same thing that it did before. All right. So that cleans that up nicely. All right, so for every offset, we'll just go through. This should be plus our offset. Okay, let's give this a shot. Still works. Let's submit that, see if this gives us any type of improvement. Not really, surprisingly. So now we're only at 44% and 64%. Wow, not making a lot of gains here. All right, what else can we do? One thing we can do this early out before we do this check. Let's do that. Swap these around. All right. Try that. Man, not making any gains here. Okay, what else can we do? We can just shrink some of this code. We could try going depth first. Let's see if that works. It still works. Let's see if this gives us any improvement. I would be surprised, but it might. Whoa, that gives us a huge improvement. Wow, look at that. So we went breadth first with a 47% for runtime, and we changed it to depth first, and we jumped to a 96% for runtime and 71% for memory. So that's a huge win. Wow, so I guess in this case, going depth first makes a big difference. Now, I don't know if I would have known that intuitively. I guess it kind of makes sense because we're only going in one direction and we're trying to get there as fast as possible. And if we overshoot, then we're just done. So that kind of makes sense, but I don't think I would have known that. Okay, well, I'm pretty happy with that one then. I think we'll leave it there. So again, this is LeetCode problem 403, frog jump, and we're doing a standard graph traversal with a depth first search. All right. Well, I hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code.